Good morning. My name is Ankunda Noella from SWML52, and our project title is a hybrid neurosymbolic causal intervention optimization approach to improving virus suppression among HIV positive youth on antiretroviral therapy. So this research combines causal inference, neurosymbolic AI, and machine learning to improve HIV treatment outcomes among the youth receiving ART in Central Uganda. Our work focuses not only on prediction, but on identifying which interventions are most likely to improve virus suppression for each patient. The contents of the presentation, it covers the problem, the background, the related work, the methodology, the 12 causal models we benchmarked, our experiential results, the deployment pipeline, the model compression and conclusions, plus the future work. HIV remains a major global health challenge, causing approximately 630,000 deaths annually, with the sub-Saharan Africa contributing most new infections. In Central Uganda, only about 44% of the HIV positive youth on ART achieve virus suppression, meaning the virus is controlled below 200 copies per milliliter. Several factors influence suppression outcomes, including the CD4 counts, the depression, the alcohol, the clinic accessibility, and traditional machine learning models can identify the associations, but they cannot answer the causal questions. What intervention should clinicians apply to improve suppression? So to address this limitation, we proposed a neurosymbolic causal AI framework that combines deep learning with interpretable causal structures. Our work builds on several major research areas. First, the Judea-Pals causal inference framework introduce structural causal models and do calculus, which enable intervention reasoning. The second, the Rosenbaum introduced propensity score methods for reducing confounding bias in observation health care data. We also reviewed the model causal AI methods such as TMLE, the causal forest, the deep 4, and finally the neurosymbolic AI combines the neural networks with symbolic causal graphs, improving explainability and clinical trust. So these studies motivated our goal to building a clinical interpretable and deployable HIV intervention recommended system. Clinically, only 43.9% of the HIV positive youth in our cohort achieved virus suppression despite active enrollment, and the clinicians often make the decisions manually, which can be slow, inconsistent, and not causal informed. Current systems also struggle to distinguish where the poor outcomes are caused by modifiable barriers like depression, adherence, and by biological limitations. From a computational perspective, the dataset is observational and treatment assignment is non-random, meaning the standard machine learning models suffer from confounding bias and Simpson's paradox. Existing systems also fail to estimate the individualized effects for multiple interventions simultaneously. Our main research question was, which causal machine learning architecture best estimates individualized intervention effects for virus suppression among HIV positive youth on ART? And to answer this, we developed 4 objectives. The first is to build a neurosymbolic causal framework. The second is to benchmark the 12 causal AI architectures on large Ugandan datasets. And the third is to estimate individualized treatments such as Operation 000, depression service delivery, and youth adherence peer support interventions. And finally, to deploy the best performing model as a web-based clinical decision support system. Our research contributions are: first, we developed a neurosymbolic architecture combining the symbolic causal DAG and your estimation module and optimization module. And the second is we conducted one of the first large-scale benchmarks of the 12 causal AI architectures in real African dataset. And the third, we formulated a constrained causal optimization framework for personalized intervention recommendation. Methodology, system architecture. Our system architecture contains the three major components. The first is a symbolic causal model, um, which encodes HIV clinical relationships with a directed acyclic graph derived from the Ministry of Health guidelines. The second is the near estimation module, primarily based on GNet and causal ML architectures. The third is the optimization module, which estimates um, the conditional average treatment effects and recommends the intervention most likely to improve virus suppression. So this architecture combines interpretability from causal graphs with predictive power of deep learning. Dataset description. Our dataset included 20,890 HIV positive youth aged 10 to 24 among 8 districts in central Uganda. We started with 53 raw variables and expanded to 60, which was after preprocessing and encoding. The dataset contained biological, psychological, structure, and programmatic variables. The EDS showed moderate class imbalance, geographic differences in suppression outcomes, strong associations between depression adherence and virus suppression. We also observed a strong correlation between the baseline and the current CD4 counts, and these findings justified the use of the causal and imbalance-aware learning methods. Those are our EDA analysis diagrams and visualizations, and we observed variation in suppression rates across districts, the skewed clinic distance distributions, and stronger suppression outcomes among patients with a higher CD4 count and lower depression scores. So these patterns reinforce the importance of modeling both biological and psychosocial determinants. So our models, model one was a Bayesian logistic regression combined with a DY causal identification. It used the Bayesian MC sampling and backdoor adjustment to estimate causal effects while maintaining interpretability. The model two combined XGBoost with EconML machine learning, causal forest double machine learning, and double machine learning removed regularization bias by orthogonalizing treatment and outcome residues, while the causal forest estimated the individualized treatment effects. Model 3 was the GNet sequential gcomputation. It modeled counterfactual outcomes directly using neural networks and achieved the highest predictive accuracy in our benchmark. Model 4 was the G transformer. It used the sequential architecture of our pseudo time steps to stimulate temporal dependencies, although its attention weights were not fully trained. Model 5 was the neural TML, which combined the superlearning ensembles with the targeted maximum likelihood estimation. This provided the double robustness, meaning the causal estimates remain consistent if either the treatment or the outcome model is correctly specified. Model 6 was the causal forest DML, and it used the honest causal trees and bootstrap confidence intervals to estimate and visualize treatment effects with a strong uncertainty quantification. Model 7 was the DR learner. It combined the outcome regression and inverse propensity weighting into doubly robust pseudo outcomes for individualized treatment effect estimation. Model 8 was a DEEP4 two-stage near instrumental variable model designed to handle unmeasured confounding. However, performance was limited because the instrument distance to clinic was weak. Model 9 was the dragnet, and it learned our shared representation with 3 output heads for propensity treatment outcome and control outcome estimation. This enabled efficient joint causal and predictive learning. Model 10 was the causal recurrent transformer, which combined the GRU sequence encoding with the causal attention mechanisms for longitudinal treatment modeling. Model 11 was a CFRNet or the TANET. It used the the Western IPM regularization to balance treated and control distributions and achieve the highest stroke AUC among the models. Finally, model 12 was the proximal causal learning, and this method used the bridge functions and proxy variables to estimate the causal effects even when unmeasured confounding exists. Together, these architectures allowed us to compare many different paradigms for the causal effect estimation in HIV intervention modeling. The results, this table summarizes the comparative performance of all the 12 models. The GNet computation achieved the best overall predictive performance with the 85.0 for accuracy and the AUC of 0.9124. The CF-RNet achieved the highest ROC and the AUC overall at 0.915 showing strong classification imbalance. Causal force provided the best confidence intervals for treatment effects, DIP4 performed poorly due to weak instrumental variables, and most models estimated positive OTC intervention treatment effects, suggesting adherence-focused intervention significantly improve virus suppression. A selected model, after benchmarking all the architectures, the GNet, it achieved a strong predictive accuracy while remaining computationally efficient and clinically interpretable. The architecture directly models counterfactual outcomes and supports simultaneous estimation of intervention effects for Operation 000, differentiated service delivery, and youth adherence peer support. It also converged quickly without requiring the GPU resources, making it suitable for deployment in low-resource clinical environments. The GNet model satisfied all the 5 deployment criteria. It achieved a high accuracy, clinically plausible causal estimates, strong recall for suppressed patients, and low computational cost. Importantly, it supports simultaneous intervention optimization. We deployed a model as Streamlit-based clinical decision support system for real-time HIV intervention recommendation. The deployment pipeline serializes the trained GNet associated propensity models using the job-lib, and the clinical inputs are preprocessed, passed through the G-computation inference engine, and used to regenerate the counterfactual intervention recommendations. The system is a Docker containerized GNet Git version and supports monitoring for covariate shift and predictive drift. Future work includes the ONNX quantization for offline edge deployment in the AMR systems, and demonstrates our deployed clinical decision support system. Clinicians input patient information, the system predicts suppression probabilities, and while recommending the interventions most likely to improve the outcomes, the platform enables real-time counterfactual reasoning for clinical decision-making. Model compression, and to support efficient deployment, we evaluated the 3 compression approaches. A first, structure pruning removed redundant neurons and reduced parameters from 5,441 to 849, while slightly improving the AUC. Second, the low-rank factorization used the matrix decomposition to compress the model weights with moderate performance trade-offs. And the third is a knowledge distillation, transferred knowledge from the GNet teacher model to the G transformer student model. Among all the models, structure pruning achieved the best balance between the compression and predictive performance. Comparative analysis, this table compares the compression techniques and structure pruning achieving the highest parameter reduction, while preserving and slightly improving performance. Low-rank factorization achieved moderate compression, but introduced some performance decline. And knowledge distillation improved the student model, but still underperformed the original unit. So these findings confirm that the original unit actually was overparameterized. And we deployed the compression technique we deployed was pruning. So because it achieved the 84.4 parameter reduction and increasing the AUC from 0.924 to 9200. And this means we significantly reduce the computational costs without sacrificing predictive quality. So this result suggests that redundant neurons were successfully removed, making the G-pruned GNet more suitable for real-world deployment. Our conclusions, GNet emerged as the best overall model, achieving a strong predictive accuracy and clinically meaningful estimates. Counterfactual simulations suggested that universal adherence improvement could substantially increase virus suppression rates. And this study also represents one of the first large benchmarks of the Causal AI architectures in African youth data set. However, the limitations remain, and some models still rely on a conformance assumption, meaning the hidden confounders could bias causal estimates. The deep four also suffered from weak instrumental variables, and current deployment still depends on the internet connectivity. Our future works will focus on integrating the model into the hospital EMR systems for real-time clinical use. We also plan to conduct prospective validation studies in art clinics across central Uganda. And finally, we aim to implement the continuous envelopes retraining pipelines that automatically adapt the model when performance drift occurs. I'd like to thank our supervisors, the college, the university, Macquarie University, and the participating HIV clinics. That's the Uganda Ministry of Health for their guidance, support, and data collection collaboration. Thank you for listening.